In this lecture, we'll cover phase analysis diagrams. The diagrams are useful in studying the phase compositions under melting or cooling of a system with a certain composition. There are two learning outcomes of this part of the course. After this lecture and working with the exercises, you should be able to construct a phase analysis diagram based on an isopletal study, and you should be able to interpret the information given in a phase analysis diagram. In order to introduce the concept of phase analysis diagrams, we'll consider an example of a real system, namely the SiO2 Al2O3 system. In the figure, we have the said system, that is the one of silica and alumina. As you can see, the diagram is plotted in mole percent, and we have a few different phases as well as a solid solution here, which is titled or named molite. So let's consider the cooling of three different compositions. And these compositions are X, Y, and Z, marked here, X, Y, and Z. When we create a phase analysis diagram for these cooling paths of a constant composition, it should include the distribution of phases at different temperatures for a constant composition of the system. And as it concerns equilibrium compositions for a constant composition of the system at a certain temperature, we can utilize these phase analysis diagram both on the cooling or melting. That is, the same diagram is showing both phenomena. So we'll utilize these three melts of composition X, Y, and Z to introduce this concept. In order to construct the phase analysis diagram, we have to make an isopletal study. In this case, we'll do it for the composition Y, which has 54.4 mole percent Al2O3, and therefore I will remove this X and Z. The only information required for the isopletal study is the distribution of phases. So therefore, we can draw this table right here, which is a condensed form of the full isopletal study. In this table, you can see that we have the temperature, we have the proportions of the phases, which will represent the measurements done in the figure, and then we have the distribution of the phases as the last column. The temperatures I have chosen as 1855, 1800, 1750, 1700, 1650, and then to the solidus line down here. So going from the first precipitation, that is the 1855, 1595 is the solidus, and then I have just evenly spaced some temperatures in between these two. So let's start with the isopletal study. At 1855 degrees Celsius, we have 0 millimeters of this that represents the melt. And I measured 6 millimeters between the liquidus line and the molite here. So 6 millimeters of melt and 0 millimeters of crystals transforms to 100% melt and an infinite small amount of molite. And we don't need the composition of the molite, and we don't need the composition of the melt. Instead, we move on to the next one, which is 1800. And for this one, I measured 5. Usually you see that we have always between the isopleth and this fixed line the same measurement, but you can see that the molite it actually changes in composition here. So therefore, this one went from 6 to 5, but it seems like we have 5 all the way down here after this. The distance between the isopleth and the liquidus line, I measured this to 16, and adding this to the table, calculating the distribution of phases, we can see that we have reduced the melt considerably to 23.8%, and we have now 67.2% molite. What we do next is that we fill in the rest of the information, and this is simply done by doing the lever rule measurements, and you know this by now, so I have just added it to the table. Coming to 1595 plus, we measure it as such that we have 44 millimeters of molite and 5 millimeters of the melt, which transforms to 10.2% melt and 89.8% molite. The last step is that this last part of the melt, it forms the eutectic crystals. So we will have 5 millimeters of the eutectic crystals, which is 10.2% of eutectic crystals. And the distribution of the eutectic crystals we can find if we take the lever rule with the line of the eutectic composition here. At this point, we can control if we have made the corrections correctly in the last row. So, for example, how much Al2O3 do we have in this? Well, we take 0.6, which is the mole percent of the molite, and we multiply this with 89.8, which is how much molite we have in these crystals, and we add the molite in the eutectic crystals, which is then 0.102, this 10.2%, times 7.7, which is this 7.7% molite, and we get 54.4% of this Al2O3. So we are still on the isoplex. Based on this information here, we will now construct the phase analysis diagram. To construct the diagram, we have two axes. The y-axis represents the temperature, and I've chosen it to be between 1500 and 1900 degrees Celsius, as this will cover all the events of our isoplateau study. The distribution is plotted on the x-axis, going from 0 to 100%, and it's simply the distribution of phases, and these phases are the melt, the molite, and the eutectic crystals. To construct the phase analysis diagram, we simply plot the distribution of the phases that we calculated in the isoplateau study. First, we'll consider the temperatures ranging from 1855 to 1595 plus, and the 1595 plus represents this composition right above the final solidification of the melt. So these points are now represented in the diagram. And as I haven't calculated the phase distribution in the temperatures between the points, I have just added straight lines. Of course, we could have added more points, for example, at 1830 and 1820 or whatever, and you could have a smoother curve, but this will suit our demands right now. Furthermore, as of right now, this is only a line, but the line, which is this line, separates the molite phase from the liquid phase. And as you can see here, in the beginning, we have 100% melt, and then going down to 1800, we should have more molite than melt. So in that case, this is the melt and this is the molite. The next information we add to the figure is the phase composition after complete solidification. This line represents the solidification forming eutectic crystals from the last part of the melt. As you can see, we have now surrounded the melt with this horizontal line, which represents the distribution in percent of eutectic crystals. As the leftmost large field right here represents molite, we have added molite in this section, separating the first precipitated molite and the eutectic molite by this dashed line. And the last field is the phase distribution of SiO2. Now this is an example taken from the course literature, and we'll briefly compare our calculations to the phase analysis diagram presented in the book. So this diagram in the book has a smoother molite line, as they have considered more temperatures in their isoplateau study. Also, the figure has exaggerated this distribution of the eutectic crystals. As you can see, this molite eutectic phase is very clear in this one, whereas in our it's not as clear, although we have a much less compressed x-axis right here. And this is simply drawn in a pedagogical way. So now we're familiar with how to construct these diagrams. To complete the lecture, we'll briefly look at the phase analysis diagrams of the X and Z composition from the first phase diagram presented in this lecture. So the figures in this slide shows the phase analysis diagrams of the composition marked in the SiO2 Al2O3 phase diagram. So we have the X, which is this one, and the Z, which is this one. You can see that they clearly represent what we have here. So for example, in the X, we have a 2% Al2O3 as composition, And when you cool this melt, the first thing to precipitate is the SiO2 crystals. And then you will have quite a large liquid phase that will solidify as eutectic crystals. And these eutectic crystals will be mostly composed of silica, and then we have some part of it that will be mullite. The second composition is that of Y, which we already went through. And the last one, Z, is 75% of Al2O3. And this is placed right here in the phase diagram. Now if we compare them, you see that when we cool it, the first crystals to precipitate is corundum, and that is Al2O3. So you see when you go down in temperature, the phase distribution of Al2O3 increases, and then you reach a point where the melt has its final solidification into the eutectic crystals, and the eutectic crystals are mainly mullite in this case, and partly Al2O3. But these type of diagrams that we have gone through in this lecture, they are easy to construct and simple to use. They can be drawn for ternary phase diagrams as well, in which case more phases can be present simultaneously. To conclude this lecture, we'll take a look at the learning outcomes again. We said that after working with the lecture and exercises, you should be able to construct a phase analysis diagram based on an isopletal study and be able to interpret the information given in a phase analysis diagram. And this information that you can get is basically the phase distribution at different temperatures upon cooling or melting. Although the learning outcome said exercises, there's actually only one exercise to solve in the book. This one is exercise 5.3. Of course, you may construct phase analysis diagrams for other binary phase diagrams as well if you wish to exercise your skills. And remember, if you have any questions, you can come by my office at any time, and you can also email me if you want us to take up some hard concepts in class. Thank you for listening.